My name's Gavin Lowe. I'm a tutor and Director of Studies for Computer Science at St Catherine's College, Oxford. This video is going to be a demonstration admissions interview. We're going to try and show you how we run our undergraduate admissions interviews for computer science, and in particular, how we run them using online technology. So with me, I've got Alistair Janse van Rensburg, who's another tutor at St Cat's, and Tom Aston, who's an undergraduate at St Cat's. Tom's just about to enter his second year. So in a moment, we'll be giving a demo interview to Tom, see how he gets on. First of all, let me just say a little bit about how we run interviews. I normally start interviews by a little bit of general discussion, try and get to know the candidate a little bit better, find out what motivates them. Sometimes at that point, I'll ask a question about something on their personal statement. Sometimes I won't do that today. However, most of the interview is made up of technical questions, some mathematical problems or puzzles to try and assess the candidate's technical ability, how well they'll cope with the computer science degree at Oxford. So for online interviews, we use an app called Miro. We'll see it in a bit. It's an online whiteboard app. My experience is that most candidates get on fairly well with that, but it's the sort of thing that if somebody messes up, we're not too worried about that. We're more interested in how good candidates are technically. So we want to see how well they cope with the problems that we give them, whether they think logically and come up with good ideas for tackling the problems. Also, are they able to explain their thinking reasonably? Of course, we don't expect a perfect explanation in real time, but I hope we can have a conversation where we get to understand what the candidate is thinking. And also the other way around, can the candidate pick up hints from us? Well, really, we want to assess whether candidates will cope well with the interactive style of teaching that we have at Oxford. So we want to see that they actually will learn from what we're saying. At the end of the interview, we normally give the candidates a chance to ask their own questions if they have any, but we won't be doing that today. Okay, so we're going to do a 20-minute sample interview. That's a bit short, really. Normally, we actually allow 30 minutes for an interview, but it's going to be a little bit shorter today. Okay, so let's see how Tom gets on. Hello, Tom. So thanks very much for coming for interview. Perhaps we can start. Can you just tell us why do you want to study computer science?
I want to study computer science because I find it incredibly interesting how an inanimate device like a computer, which fundamentally built up from silicon, can sort of work from the very smallest elements like transistors all the way up to, for example, Teams that we're doing this interview over, and how that can sort of be abstracted out from small logic gates up to adders, up to applications and operating systems.
Okay. Can you tell us about something interesting you've done in the area of computer science, maybe an interesting program that you've written?
Although it's quite simple, probably my favourite program that I've ever written was just a small minimax algorithm for noughts and crosses. It's yes, it's quite simple and the implementation wasn't too hard, but I found it really neat how an algorithm like that can be implemented and how you can basically create an unbeatable AI for a game as simple as noughts and crosses.
Okay, that sounds interesting. Thanks. Okay, so let's move on to some technical problems. So for the purpose of the recording, I'm going to share my screen looking at Miro. Okay, so there's a question here. So let me read the first bit through to you, Tom, and then you can have a go at it. So Alice plays a game with her friends Sam and Pam. In each of the scenarios below, she chooses two positive integers x and y, so 1 less than or equal to x less than or equal to y, and she whispers the sum s, which is x plus y, to Sam, and whispers the product p, which is x times y, to Pam. Sam and Pam have to try to work out what X and Y are. They're all expert logicians and they always tell the truth. Okay, so part 1, Alice chooses two positive integers X and Y as I just described and whispers the sum to Sam and the product to Pam. Sam says, I know what X and Y are. What can you say about X and Y?
Okay, so for Sam to know what X and Y are, then X plus Y must specify, well, S must specify two distinct integers. I think the most obvious initial case is if S is 2, because then that just gives X is 1 and Y is 1.
Mm-hmm.
Would there be any case beyond that? I think if S is 3, then that also precisely specifies X and Y. So we have X is 1 and Y is 2.
Yeah, that's right.
So 2 equals 1 plus 1, 3 equals 1 plus 2. But then beyond, I think those are the only cases, because 4 could be either 1 and 3 or 2 and 2. So it doesn't give us the exact.
Yeah, that's right. Sam won't be able to work out in that case. And for larger values of S?
That would hold beyond, because any large number of S can be 1 plus, sorry, that should be S minus 1,
Mm-hmm.
or
similarly with 2.
Yeah, or similarly with 2.
Yeah, no need to write it out.
Exactly.
Okay, good. Let's have a look at part 2 then. So Alice now chooses new values for X and Y and whispers the sum to Sam and the product to Pam. Pam says, I know what X and Y are. What can you say about X and Y?
So in this case, we have X and Y precisely specifying P, which means that P must only have 2 factors, because otherwise we don't know what X and Y are, which tells us that P must be prime. And if P is prime, because we have X is less than Y, well, X has to be strict, well, less than or equal to Y, but since it's prime, we know X is less than Y, so we know that X must be 1 and Y must be the value of S that Sam's told.
You mean the value of P that Pam's told?
Yeah, the value of P that Pam's told, sorry. Which means that the value that Sam is told is P plus 1.
Right, so
yeah.
So does Sam now know what X and Y are?
Yes, so Sam knows that X equals 1, and shift again, and Y is S minus 1.
Yeah, that's right. You actually missed a little bit with Pam. Normally the number 1 is not considered to be a prime number.
Yeah, sorry.
So if actually P is 1, then X is 1 and Y is 1, fairly obviously. But yeah. Okay, good. Part 3. Alice again chooses new values for X and Y and whispers the sum to Sam and the product to Pam. Pam says, I don't know what X and Y are. Sam then says, I know what X and Y are, but I didn't know before Pam said that. Okay, so first of all, can the sum be less than 4?
No, the sum can't be less than 4, because in part 1, like the minimum sum's got to be 2, and in part 1 we saw for both S equals 2 and S equals 3, that tells Sam precisely the values of X and Y, i.e. that he knows the values of X and Y before Pam says that they don't know what X and Y are.
Yeah, that's right. If the sum's less than 4, then Sam would know immediately. Okay, part B. Suppose the sum is 4. What are X and Y?
So if the sum is 4, then that either gives X equals 1, Y equals 3, or X equals 2, Y equals 2. So Pam doesn't know what X and Y are. However, well, so in the case that x equals 1, y equals 3, then Pam knows that p equals 3. And in the other case, Pam has that p equals 4. If p equals 3, then Pam's been given a prime number, which means that she knows the values of x and y. However, since she doesn't know what the values of x and y are, we must therefore have that x equals 2 and y equals 2.
Right, so by the fact that Pam doesn't know what x and y are, we can eliminate x equals 1, y equals 3. And in the case of, so how does Sam now know what x and y are?
Well, Sam knows that sum is 4. So in effect, before Pam says anything, Sam knows that. So either x equals 1 and y equals 3, or x equals 2, y equals 2. And in this case, when Pam says that I don't know what x and y are, that gives us the additional knowledge that therefore p cannot be 3.
Right.
Because in that case, she'll know. Therefore, we know that it must be p equals 4. So x equals 2, y equals 2.
Yeah, good. Okay. Part C, can the sum be 5?
So if we consider s equals 5, then that would give x equals 1, y equals 4, or x equals 2, y equals 3, as the only cases to consider is x must be, well, less than or equal to y. So is that, yeah, can this, wait.
So
Yeah.
you consider those two possibilities. Are they consistent with the story?
So in both cases, well, first one gives p equals 4, the second gives p equals 6. If p equals 4, then Pam doesn't know what x and y are again, because we also have x equals 2, y equals 2. And then if p equals 6, then Pam also doesn't know what x and y are, because we could alternatively have x equals 1, y equals 6.
Right.
So Sam doesn't gain any information from that.
Yeah, that's right. So in both cases, Pam would say, I don't know what x and y are. So Sam doesn't learn anything from that. Okay, part D then. Can the sum be more than 5?
So if the sum was more than 5, then we would have at least 3 pairs of x and y to consider.
Right.
Because, so s equals, let's say 6 as an example, but it would hold, then we have x equals 1, x equals 2, x equals 3, all to consider. So when Pam that's what it work for x. S equals 6. So no, sorry. Y equals 5. Y equals 4. Y equals 3. Which gives p equals 5. P equals 8. And p equals 9. If we have that p, so in this case, actually, yeah, in this case, the additional knowledge that Pam doesn't know what x and y are doesn't actually help, because if Pam knows what x and y are, we have that x equals 1 and y equals 5 because 5 is prime. However, the other two possible values aren't prime, so that doesn't actually tell us anything additionally.
Right. So at least those latter, the cases x equals 2 and x equals 3, Pam wouldn't know what x and y are.
Yeah.
So.
Oh, yeah. So Pam only knows what x and y are when, without any additional information, when x is 1. However, since x is less than y, x is 1 only occurs once. So the additional knowledge that Pam doesn't know what x and y are only eliminates the x equals 1 case every time. However, for s equals 6 and above, we always have at least 2 further cases to consider. So it doesn't actually, it doesn't tell us sufficient information to figure out x and y.
Yeah, that's right. So in each case, it'd be at least 2 possibilities where Pam doesn't know what x and y are, and Sam won't be able to tell the difference between those. Okay, so to actually summarize question 3, the only solution we got there was x equals 2, y equals 2 happens to be the only solution to that. I think what I want to do now is skip part 4 because we're actually quite tight on time, but we can go on to question 2 and I'll hand over to Alistair. So you'll all need to advance on the PDF. So Alistair, if you want to take over.
Okay. Tom, can you see the second page of questions there, starting with consider the following list?
Yes, I can now.
Excellent. Okay, I'm just going to read that out for you, and then we'll talk about the questions below. Consider the following list of 5 numbers, 1, 3, 2, 4, 9. For some numbers, 1 less than equal to A, less than equal to B, less than equal to 6, we're going to define the sublist from A to B to be the consecutive numbers from the list, starting at position A and up to but not including position B. So, for example, if we wanted the sublist from 2 to 5, that would be 3, 2, 4. And the sublist from 4 to 6 is 4, 9. And so that's the 6 going off the edge there, but we're just ignoring that there because we want up to the last one. And then the sublist from 1 to 2 is just the element 1. And then finally, just as a convention, we're going to say the sublist from x to x, for any x there, is defined to be just the empty list there. We're also going to say that S of A, B is going to be the result of adding up all the elements of the sublist from A to B. So the first question I want you to answer here is, how many sublists are there that start from the first element?
Starting from the first element, there would be 5 sublists.
Okay, can you just go through what those would be?
Sure. So you have first one is going to be the empty list.
Okay.
Then just the first element itself, first 2 elements. Let's put in the brackets. First 3 elements. So 1, 3, 2, and finally first 4 elements. 1, 3, 2, and 4.
Okay, why have you stopped there? So if you just look at the definition, there we can go up to 6. Yeah,
we can go up to the last one. Sorry. So
yeah, exactly. But you have spotted that the empty list is one of those lists there, so that's good. Okay, so now how many sublists are there starting from any element, not just from the first one?
So from any element in this list, if we from any element in this list, it would be well, from the first element we have 6.
Yeah.
Like 6 sublists. From the second element, we'll have an empty list, a list of 1, a list of 2, a list of 3 of length 3, and a list of length 4, but not a list of length 5.
Yep.
So in this case, the total number of sublists from any element would be 7 minus n, where we let n to be the position or index. Yep.
Okay. Okay, so if you add all those up, you're going to get some number there. Have you double counted any lists there? So do you have any lists in those set of lists that would be the same?
when you say in that set of lists, what do you mean by that?
So for instance, your list starting from the first element there, you have the empty list and then 1 and then 1, 3, etc. What are your elements starting? Sorry, what are your sublists starting from the second element?
From the second element, the empty list will obviously be the same. But then otherwise there wouldn't be any overlap with the elements in the first one. So it'd have empty list. 3.
Yeah, okay, that's good.
3, 2.
So can you spot the duplicate there, where you have two lists that are being counted, or rather one list that's being counted twice?
Yes, so the empty list.
Excellent. Okay, yeah, so we can count that and get rid of that. But okay, so moving on to question 2 here then. Can you tell me what the value of S26 is? That's the sum of the elements of the list 26, sublist 26.
So the sublist 26 involves starts from index 2. So that would be 3 plus third element 2 plus the fourth element plus the fifth element, which works. So 3 plus 2 plus 4 plus 9 is 18.
Excellent. Okay. So now what we want to do is do a bit of manipulation with that. So we've got an expression there in part 3 there. So it says S of AB is S of 1B minus S of 1A. Can you explain to me why that expression is true?
Okay. So, okay. Just trying to think how one's this. Right. So if we have okay. So in effect, the value of S of A can be, if we just draw out our list currently from 1, 3, 2, 4, 9. If we let but basically the sublist, well, the value of S from 1 to B obviously includes all the values from 1 to B, and yes, the sublist, the value of S brackets 1 comma A includes all the values from 1 to A, which means that all the values less than A all the values of index of less than A are included in both the summation from 1 to B and also summation of 1 to A.
Yeah.
So then as a result, they get like the subtraction effectively removes them.
Yeah, exactly.
So yeah, the only values that aren't then eliminated are the values that occur from index A onwards in the expression.
Yeah, up to B. Yeah.
1, B.
Yeah, that's good. All right.
Therefore, that's why they're equal.
Yeah, excellent. Okay, so part 4 here.
I'm afraid I'm going to just pop in at this point. I'm afraid we're basically out of time at this point. We've had our 20 minutes and we never get through all the questions, so don't worry about that. But thank you very much, Tom, for that.
Thank you.
Bye for now.
Bye.
Thanks.
Okay, so I think Tom did very well there, generally. I sort of expected that. Tom's already been interviewed once and he got a place on the basis of his interview. So he's already shown that he is very good, has the sort of skills that we're looking for. In addition, he's now about 2 years older and has 2 years more experience than when we first interviewed him. And hopefully he's learned some things in that intermediate time. He didn't answer all the questions in the time available, but we pretty much expect that. In addition, we only gave him 20 minutes, whereas normally we'd allow 30 minutes for an interview like that. So anybody who gets about that far in 20 minutes is almost certainly going to get a place. So he did very well, and we're not really expecting all candidates to do that well. In particular, one thing he did very well was just not to get modelled. It's quite common particularly the first question we asked there, for candidates to just get completely stuck for a bit or to spend time going around in circles. A common thing that people do is actually repeat the earlier parts, forgetting that they've already solved a particular subproblem and go back and solve it again, even though effectively they're just repeating an earlier part. One thing with hindsight I should have stopped him doing is that he rubbed out his answers to each of the individual parts. Actually, it would have been a better tactic for him to have left those there so that he could refer back to earlier parts when answering later parts. Yeah, so generally he did very well, understood all the questions well, thought very clearly. There were a couple of bits where he was just a little bit slower. He was in the second question with Alison, he was a little slow to spot that the empty list was repeated, but we expect the odd oversight like that. And his final explanation might have been a little bit clearer. I think it's the best way to answer that question is to draw a picture highlighting the different regions, the different parts of the equation represented. But these are sort of minor criticisms, and overall, that was a good performance. That's the sort of performance that would normally get somebody a place in Oxford. Okay, so I hope this video has been useful and interesting to you and helpful to show you how we run these sorts of interviews.